Welcome to CS 320, Chapter 6 on transition graphs. So if we take a finite automata that we learned about in the previous chapter, and we try to relax the rules to maybe make it easier to create. So there's a couple of things with finite automatas. One rule is that you can only read one letter per edge. That means that you can't put two letters on an edge and read two letters off of your input word. So with a transition graph, we're relaxing some of those rules, and that allows us to read two letters at the same time. So if our word begins with BA, then we can follow this edge and land in this state. Or if it starts with an AA, then we can follow this edge and land in this state. So every transition from one state to another state can read multiple letters. Now, a common thing with finite automatas is having some state that is a rejection state, where you've broken, you messed up, you definitely do not have a word in the language, so you end up following an edge to a state that finishes and reads the rest of the letters in the word and ends in a non-final state. I've called this state outer darkness before. We're kicked out, there's no getting into the final state. So with transition graphs, if we want a transition graph that accepted only the word BAA, we might make a machine that looks like this. So if we read BAA, we go to the final state, but if there are any following letters, we get kicked out into outer darkness. Now, what do we put on this edge right here? Well, basically, it's just anything but BAA. Now that would be a lot to write, all the different options of reading three letters that are not BAA. So what we can do with transition graphs is actually erase all of this. And now what we have, if we have the word BAA, then we can start in this state and read our BAA off of our input word and land in the final state and accept the word. But if we have a different word like ABA, or maybe even just A or something like that, when we're in the start state, we don't see an edge that we could follow for either of these two words. And so since there's no edge to follow, what happens is the machine crashes or just rejects the word. If there's not a path to follow from one state to another state, then that word is not in the language automatically. So we don't need that outer darkness state. Now let's take this transition graph. Let's say that we have the word B, A, B as our input word. As you can tell, we have this start state and we have a choice. Our word starts with the letters BA, so we could follow this edge to this state right here, or we could follow this edge to this state right here. Now you can't do that with a finite automata from chapter 5. There's no going to two different states. So if one person is doing the machine, they can say, oh, I'll take this edge, and another person says, oh, I'll take that way. You can't do that with finite automata. With finite automata, every person running the machine has to choose the same edge because there's only one A or one B to leave the state. But now with a transition graph, we have a choice between landing between those two states. So let's go ahead and say we chose this edge. So we read the BAA and we arrive in this state. Then we see an AB following that and we arrive in this state. And that's a final state, so we accept the word. But what if someone else ran the machine and they read BAA and they got to this state, and then they read the AB and they got to this state right there. And they say, oh, nope, that word is not in the language. So who's right? So with transition graphs, as long as there is one way to start at a start state and arrive at a final state and read all the letters in our word, then that word is in the language. So even though there's another path that might not lead to a final state, the word is still in our language because there's at least one path that does. Now, what that is called is non-determinism, meaning there isn't a set way that everybody has to follow or run the machine. Some people might choose to run it this way, and other people might choose to run it the other way. But as long as there's a way to go from start state to final state, then that word is in the language. Now, our processors, our CPUs today, are not supposed to be non-deterministic. Could you imagine if you ran a program and sometimes it did one thing and other times it did another thing? Programs are supposed to have the same result every time you run it. Now that is, of course, if you don't have random numbers getting generated causing it to do different things each time. So for the most part, processors are supposed to be the opposite of non-determinism, and that is deterministic. So our CPUs today should be deterministic, but these transition graphs happen to be non-deterministic. Now, something else that we can do with transition graphs happens to be a null transition. What that means is we can move from one state to another state without reading any letters off of our input word. So we don't read any letters, we just read an ABB off of our input word, and that puts us in this state. Then we can jump to this state next, or we couldn't. Now this again is non-deterministic. So somebody could decide, okay, I've read ABB, I'm jumping to this state. And then the next letter I read is an A, and that's the final word. Whereas someone else might say, I read ABB, and I decide not to take this transition. I'll stay in this state right here. And when I read my A, there isn't any path, so that means I reject the word. Of course, the word is accepted because there was one way to get to our final state. And the final thing that we can do with transition graphs that we cannot do with finite automatas is have multiple start states. In a finite automata, you can only have one start state, but here we can have multiple start states. And that means that this finite automata accepts the word A, B, or ABA. Now, another way that we can do this is create one start state and have a null transition to any one of those three states. And then we can erase the start state inside of each one of these states. And so those two transition graphs are exactly the same. So we can have multiple start states and save us the trouble of having to draw all of this. Now, once again, just like with finite automatas and regular expressions, we have a new way to define languages called transition graphs, and there's going to be two things that you'll need to do. One, look at a transition graph and decide what language it accepts, so come up with an English description of what this language accepts. And the other thing is doing that in reverse, taking a description and generating a transition graph. So if we look at this transition graph, we can read letters as much as we want and then read a B and land in our final state. If there are any letters after that B, then we'll fall off the edge and crash. So this transition graph is all words accepts the language, all words that end with a B. Okay, now what if we were to make a finite automata that accepts this? Now, first of all, let's look at a couple of reasons why this is not a finite automata. First of all, we have some non-determinism here. If we're reading a B, we can either take this loop or take this edge. That's not allowed with a finite automata. Another thing, this state right here has no edges exiting it. To be a finite automata, it would need an A and a B edge to leave it. So how would we do a finite automata that accepts the same language? And what we need is a start state. And then while we read A's, we'll be there. If we read a B, we'll go to a final state, and we'll stay in that state while we read B's. And then if we read an A, we'll go back to the start state. So as we read our word, we'll kind of bounce between these states, maybe taking a loop a few times. And then if our word ends in a B, we'll end up in this state, either through that way or by reading multiple B's, and we'll set the word. If the word ends in an A, then we'll come back to this state or maybe stay in that state, and we will reject the word. So this is a finite automata that accepts the same language as this transition graph. Now, another thing, all finite automatas are also transition graphs. So this can be considered a transition graph as well. Now I'll leave you with one more example. What if we wanted a transition graph that accepts the language even? How would we make that? Of course, one answer is the finite automata that accepts even that we studied in the last chapter, because all finite automata are also transition graphs. Now, a simpler way would be to have a start state. And while we read letters of 2, AA or BB, we have an even number of A's and an even number of B's. If we read an AB or a BA, we'll go to this state over here. And then while we read an even number of A's and an even number of B's, we'll stay in that state. And so this means we have an odd number of A's. This state says we have an odd number of A's and an odd number of B's. And then as we transition back with an AB or a BA, now we're back to even. Now, what about words that have an odd number of letters? What if we don't have 2 letters to read? We're at the very end of the word and there's only 1 letter left. That's going to force us to have an odd number of something, and we would end up crashing off of this machine, either in this state or in this state. So that wouldn't be a word in our language. So that's a quick summary about transition graphs. There's lots more examples in your book to get a better idea of how to build these and how to use these. Thanks for watching.